My name is Rina Manya. This is Group 34, and our project is about glaucoma detection, especially for people that use a lot of makeup. So this is our exploratory data analysis. Yeah. Briefly, exploratory data analysis is the process of analyzing data sets to summarize their characteristics before modeling. It helps us to understand the structure of a data set by exploring and cleaning it before we apply any machine learning models. Yeah. So let me explain about the code. Um, the first line, we import pandas library, which is used to handle and manipulate the in tabular form. NumPy is also imported as NP, and it's a library that provides support for numerical computations like working with the arrays and mathematical operations. Matplot library, it's used for creating graphs and visualization. Import Seaborn is a visualization library that is built in Matplot library, and it helps to create more visually appealing plots. We import label encoder from scikit-learn, and it converts categorical data into numerical values for machine learning models. Then we import the principal component analysis from sklearn, which is used to reduce the number of features while retaining most of the data's variability. Next, we import the Spearman function, and it calculates the Spearman correlation coefficient and helps to detect relationships between numerical variables. Yeah, and the next part, we read the data set to ensure that we are to ensure that we handle the commas correctly. It reads the CSV file that is located in this directory, and the skip initial space ensures that if any column names have leading spaces, they are ignored. So now let's go deep into understanding the data that we are working with. Print data.head displays the first 5 rows of the data set, which helps us to get a quick preview of the data. Then print.info displays the information about the data set, like the number of rows and columns, then the data types of each column, and then maybe the number of columns with missing values. Print data to it displays summary characteristics for the numerical columns, like the mean, standard deviation, then the percentages, and maybe the minimum and maximum value. Data.non-unique, it shows the number of unique values in each column and helps to identify categorical columns and high cardinality features. So now let's go into cleaning the data. That is maybe dropping the unnecessary columns. So in line 19, we remove the glaucoma type column from the data set, and in place equal to true means that the change is applied directly to the data immediately after removing the data column from the glaucoma type column from the data set. The next line, which is line 22, it removes the medical history column from the data. I'm going back to line 19. This one in our data sheet, we had some individuals whereby they were not diagnosed with glaucoma, but then on the glaucoma type, that was a type of glaucoma that they are suffering with, which is unrealistic. So to solve that, we had to write this instruction for that column to be, for the column with the type of the glaucoma to be deleted. Yes. And then the next line 25, it displays the updated list of the column names after dropping the unnecessary ones, like the glaucoma type, and then also the medical history of the data set. The next line, which is line 28, it checks if the glaucoma type is still in the data set, and it should return false if the column was successfully removed. Yeah. Then the data, the next line, which is line 32. Yeah, line 32 replaces the missing values, the medication usage column with the string unknown. That is it. Let me give a chance to my fellow colleague to take you through the next code. Thank you very much.
I'm going to continue with our code. What my colleague did talk about that I would want to add on, I think is a part of the glaucoma history, where we dropped the medical history. When we calculated the missing values, when we're understanding our data, we noticed that the medical history and medication usage have very many non-values, like they have very many space there. And since we are cleaning our data set, we do not need to have very many parts that have missing values. So what we did, we prioritized which one we don't need. We need most and the one we don't need. So we noticed that the medical history, first of all, had very many gaps than the medication usage. So we dropped the medical history and filled in for medication usage. The part where we had it now, we filled in unknown. So as we continue, you realize that we identified the categorical features. Why do we identify categorical features? Because when you're training our model, we mostly train it on numerical data. We are going to use numerical data. We are also going to use images. So the fact that I've gotten first for the statistical data need to get the numericals or the categorical. So this is the categorical code, the one that identifies the categorical features. After identifying them, we need to check for the unique values in the categorical column, and then we clean them. Yes. So this is the code for cleaning them. And then we join them into a multiple. Now, for example, this code, when you see it, you have to join it into one. Yes, then after that, I'm going to show you the output and explain the different outputs for the different codes that we're talking about. I just wanted to run through the code and show you what it means and what it is doing. So after getting the unique values in the categorical columns, we need to identify high cardinality. The high cardinality means having many unique values. Having very many unique values makes us get very many different data sets. For example, we can be having like very many columns. Originally, we just have 5 rows and 17 columns. I'm going to show them to you. But if we do not check for the cardinality, we can end up having very many columns. Yes. So yes, we identify the high cardinality from this code. And then how do we solve high cardinality? We use label encoding. How do we solve low cardinality? We use one dot encoding. Yes, it is right here. Yeah, so I did the label encoding after identifying the high cardinality column. I identified the low cardinality and still did the hot encoding. Then after I identified the numerical columns, then I assigned a function to it. Yes. Identifying the numerical column. And then I put them in a list. So I can now see that I'm having numerical column from the categorical column. So as you're performing EDA, we also need to identify outliers. I define outliers as data points that differ significantly from the data. For example, if I'm having a column that has edge, and the edge I'm having is from, let me say 20 to 70, and then at a certain point in my data, I have a 170. That is an outlier. So I need to handle such outliers because most data sets have outliers, and I noticed mine has. So how do I handle outliers? I use the IQR, interquartile range. Then, as you remember in math, we have the upper quartile and the lower quartile. After doing that, the lower bound is the same as the lower quartile, upper bound is the same as upper quartile. That's how I understood it. So I get the lower bound, the Q1 minus 1.5 times IQR, like the interquartile range that I wrote, which is the Q3 minus Q1. Why do I use 1.5 times IQR? And it is a common statistical rule of thumb. That's why we use it. So how this works, the lower bound, any value below the lower bound, considered an outlier, and any value above the upper bound is also considered an outlier. So after I identify the outliers, I cap them. Now, there are different methods of handling outliers. You can delete them, but me, I decided to cap them. I decided to get those that are above the lower bound to be capped to the lower bound, and those that are above the upper bound to be capped to the upper bound. Then after that, I returned the data. But then, the one handling the outliers, I need to what? I need to handle it for also the numerical column. So I get that function and I give it to the numerical column. Yes. Then after that, I checked for the missing values, to have an outview of my data set, how it's looking like after all the functions, the commands that I had performed on it. Yes. Now, my colleague talked about Spearman correlation, and we got the library to perform the Spearman correlation, the multicollinearity. This detects and removes highly correlated numerical data. So this, we are using 0.9 as our threshold, and this set will store the column names of the features that have a high correlation. Yes, the set ensures that no feature is added multiple times. Yeah, then I identified we already got the highly correlated point, and then after that, we dropped them. The Spearman correlation. Yes, maybe to add on something, why do we use the threshold of 0.9? Is because the absolute correlation between two features, if the absolute correlation between two features is greater than 0.9, we need to drop one. Yes, because it means two features are nearly identical. Yeah, that's how I understood it. If two features are greater than, if they're greater than 0.9, then they're highly identical. So we need to drop one place. So I got it right there. Then perform the physical component analysis, and introduces dimensionality, reduces redundancy, and also improves the computation efficiency. That's why we do principal component analysis. And then we need to display the updated data frame after processing, like after all the coding that has happened. That's what I'm doing on this two line, on this three line here. I get that I think I actually told you that data.head gives you the first five rows. So we need to see how they are. And then we also need to see the number of columns that we finished encoding. Yeah, and then they'll come there. So we use the heat map to visualize the correlation matrix. Yes, and you set it to length. Yes, you set it to length 12 and width 8. So we had, I think I'm going to show it to you. Let me run the code. Map the correlation for the correlation matrix. So here, each value, I think the diagonal, each value is perfectly correlated with itself. Okay, that's what that means. Then the values that are close to +1, the values that are close to +1, as you can see, means they mean a strong positive correlation, and those are the ones in blue. Then those that are -1, they mean a strong negative correlation. That's what, and then 0 indicates that there is no correlation. In the code. I want to explain the output. So as you can see, I think my colleague told you that the data.head will give you the first 5 rows and they're here. And then everything here, as you can see, the data.head, data.info, describe, and then it will show us that we have 5 rows and 17 columns. It is showing us that we have 10,000 entries from 0 to that. We have a total of 17 columns. And then the describing is where I will show you then the entries that we have, the null, the non-null. Yes, so the patient ID always have all the entries. The patient ID is an integer, some are objects, some are floats. As you see, when I told you about the medical history and the medication usage, as you can see the percentage that this one, the medication usage has, sorry, the medical history has a higher percentage of having a lot of space, a lot of unassigned to values. That's why we dropped the medical history. But for the medication usage, we filled in the space. Give us the total number of the floors, the total number of the integers, and the, yeah. Here where we have print glaucoma in data.columns, we have none. It has showed us that it drops the glaucoma type, the column itself. Then we printed this is showing us the column names in the data set. Yeah. The command that shows us the mean, the standard deviation, the 50%, 70%, 75%, that. So the column names after dropping the medical history and the glaucoma type, they are there. As you can see, it is no longer there. Medical history was here, it's no longer there. glaucoma type is also no longer there, just to confirm that all the columns that I didn't want to be there are dropped. Yes. Then remember when you talked about the categorical columns, where I wanted to first get the categorical columns, the ones that are categorized. Then I also needed to get the unique values in the different columns. As you can see, there are unique values in gender and all that. Because that is just showing the unique values as the output for getting the unique values, checking for uniqueness in the categorical column, so that you can clean them. Yes, let's put all that. Then the high cardinality, remember when we talked about identifying the ones with high cardinality, there are those ones. And then we worked on them. So the numerical columns were those. As you can see, the number of outliers in the different columns, we are seeing them that we handed them, all of them are 0. Then yes, the missing, we need to check for the missing values because it helps us as we are training our model to have us like computational efficiency. You can see the missing values are awesome now. Then the highly correlated features drop, they show you that they're empty. Then the PCA we conducted, the PCA, as I said, PCA is used for dimensionality and improving the computation efficiency. So that is the updated data frame after the PCA. Yes, it's just showing us the first 5 rows. Yes, and then the numbers of columns after encoding, they were still 17. So we made sure we did not have, as we were coding the first time issue, we got there's a time of we have that very many columns after the encoding, but we reduced it up to when we had the normal data set that we had before. Yes, thank you so much. One thing I also want to add in is that our project is a glaucoma detection, and we are doing 2 parts. We have 2 data sets. We have the statistical and the image based, but we first made the EDA on the statistical, and we are going to also do on the image. Thank you so much.